Dear student, in the last class I explained LCR circuit quality factor and then I solved problems. Today we continue that one, and here before taking transformer, LC oscillation etc., I want to tell some of the basic points on different types of circuits that you can expect in annual exam as a problem. The first one is LCR circuit. In LCR circuit, R, L, C, all of them are in series, and Z is given by square root of R square plus XL minus XC whole square, and phi is equal to tan inverse of XL minus XC by R. It is the general formula what I wrote, remember. Okay. Now think that in a circuit, inductive reactance is more than capacitive reactance. XL greater than XC, then Z is equal to square root of R square plus XL minus XC whole square. Phi is equal to tan inverse of XL minus XC by R. And whose property dominates? Inductor property dominates. What is the property of inductor? V leads I. It is always true. Next, another possibility, if inductive reactance is less than capacitive reactance, if inductive reactance is less than capacitive reactance, Z is equal to square root of R square plus XC minus XL whole square, and phi is equal to tan inverse of XC minus XL by R. We can write, because capacitive reactance is more, XC minus XL by R, and whose property dominates? Capacitor property dominates. What is that? I leads V, current leads voltage. Now, instead of this formula, let us say you are writing this formula in this case, second case. Second case, let us say you wrote tan inverse of XL minus XC by R, then XL is less, XC is more. Is it not a negative? Yes. So phi becomes a negative. Whenever phi is negative, you simply say that I leads V. That also you can do in the annual exam. No mark will be deducted. Okay. Third possibility, if inductive reactance equal to capacitor reactance, then it is electric resonance. Z is equal to R and phi is equal to tan inverse of, this difference is 0. Therefore, tan inverse of 0 is equal to 0 degree, means V and I are in phase. Now, in this LCR circuit, think that capacitor is removed. If capacitor is removed, what are the components remaining? R and L. It is known as RL circuit, like this, RL circuit. We can expect problems on this. And it is the phasor diagram for RL circuit. This is current I naught through both of them, and voltage across resistor is in the same direction. It is the peak voltage across resistor and peak voltage across inductor, which is leading by 90 degree with respect to current. And Z is equal to, it is the square root of R square plus XL square. Forget about capacitor reactance. This term is neglected, it is 0, it is not there. Therefore, it is XL square. And phi is equal to tan inverse of, neglect XC. Therefore, it is XL by R, tan inverse of XL by R. And whose property dominates? Inductor property dominates. What is the property of inductor? V leads I. Always. Therefore, you can expect one more question. Mention the circuit where voltage always leads the current. Then you can write this. It is the RL circuit where voltage always leads current. Okay. What is another possibility? From this RLC circuit, let us say L is taken out. If L is taken out, what are the components remaining? R and C. So it is RC circuit here, RC. Both of them are in series and it is the phasor drawing. Look here, it is the current I naught, current is same, peak current, and voltage across resistor is in the same direction as current, but voltage across capacitor is lagging behind by 90 degree. Therefore, in the case of capacitor, current and voltage are 90 degree out of phase, and this is applied voltage. Okay. What is the equation for Z? Look here, here inductor is missing, therefore neglect this term, neglect inductive reactance, that you take it as 0. Z is equal to square root of R square plus XC square, and phi is equal to tan inverse of XC by R. And whose property dominates? capacitor property dominates. What is that? I leads V. Always current leads the voltage. Therefore, even though you are studying LCR circuit, you can expect problems on these two, very, very important one. Now, we discuss LC oscillation. So, what is LC oscillation? It is very important one. So, LC oscillation means, before discussing LC oscillation, I want to explain what is the meaning of this by taking the oscillation of simple pendulum. So, it is by comparison we will get lot of information about LC oscillation. So, if you take simple pendulum that you studied in first PU, let us say simple pendulum is made to oscillate. Whenever it is oscillating, then there is a change in the type of energy, remember. Total energy is conserved, remember, total energy is kept constant, but kinetic energy and potential energy, they change periodically. So, think that simple pendulum is oscillating. Between the two extreme points. Okay. Now, this is known as the mean position. These two points are known as extreme position, and it is now oscillating, remember. Then we know at the mean position it has got maximum velocity, because at the oscillation whenever it crosses here it has got highest velocity. Therefore, here kinetic energy is maximum and we say potential energy is 0. Got it? Now, what is the formula for kinetic energy? Here kinetic energy is given by the formula half m v maximum square, where maximum is the velocity whenever it crosses the mean position. And what about kinetic potential energy? 0. And we know total energy is equal to, it is sum of kinetic energy plus potential energy. It is always constant. But think that it goes to the extreme position. At the extreme position, velocity is 0. Therefore, what about kinetic energy? 0. And potential energy becomes maximum. Potential energy is given by the formula half m omega square A, where A is the amplitude, remember. Okay. And then total energy is again kinetic energy plus potential energy, it is a constant, remember, half m omega square A. Now, here also if you are interested, you can find out V maximum. What is the formula for V? V equal to omega into square root of A square minus y square. At the mean position, y equal to 0. Therefore, V maximum is equal to omega into A, because y is 0. Okay. Therefore, what about maximum kinetic energy? Maximum kinetic energy is equal to half m V maximum square, that is omega square A square. Therefore, this is also equal to half m omega square A square. So, total energy at the mean position is also equal to total energy at the extreme position, remember. Okay. Now, see here what is happening. Whenever it goes from mean position to extreme position, kinetic energy goes on decreases, potential energy goes on increases. Here total energy is in the form of kinetic energy, here total energy is in the form of potential energy. From one form of energy it becomes another form of energy. And can simple pendulum bob remain here? No, it comes back. As it is coming back, again potential energy goes on decreases and here it becomes kinetic energy. So, therefore, during the oscillation, kinetic energy and potential energy, they keep on change, remember, not total energy. To the another side also, if it comes in this direction, again as it comes in this direction, kinetic energy decreases, potential energy increases. Therefore, at the extreme position, again kinetic energy is 0, potential energy is maximum, that is a half. Okay. So, here again total energy is kept constant. Okay. So, during the oscillation, the energy changes its form, remember. energy, it continuously changes its form from kinetic energy to potential energy. Now, in LC oscillation same thing is happening. At one instant energy is stored in capacitor, later energy is stored in the inductor. Here at the another extreme kinetic energy is 0, potential energy becomes maximum, total energy is kept constant. Now, same thing happens in LC oscillation. In LC oscillation there is a transfer of energy from capacitor to inductor and inductor to capacitor. So, there is a continuous transfer of energy and in the process alternating current is produced in that circuit. With the time it automatically produces alternating current, hence it is known as LC oscillation. When capacitor is fully charged, then the energy stored in capacitor in the form of electrostatic energy, and after some time the total energy stored in inductor, that is in the form of magnetic field. Therefore, electrical energy becomes magnetic energy and later from the inductor again it is transferred to capacitor to the form of electrostatic energy. So, there is a transfer of energy between these two. It is similar to the transfer of energy from one form to another in the case of oscillation of simple pendulum. Now, we discuss about LC oscillation. So, how to study this one? Here it is very clear, we require inductor and capacitor. So, now let us say here we take one capacitor, let us say it is the plate A, this is the plate B, and here inductor, we take inductor. Here we take power supply, DC power supply or battery, cell, such that here you have got three separate terminals. These are the three terminals. Let us say connecting terminals, this is let us say X, Y and Z. And to make it clear, let us say I am taking this as a 6 volts battery. It need not be 6 volts, it may be 10 volts, 3 volts, anything. Okay. Now, this is capacitor C and it is the self inductance L. Now, in the beginning we join both X and Y. If you connect these two terminals, then it is as good as the capacitor is connected to the cell of 6 volts. We know when capacitor is connected to the cell, immediately it starts to acquire charge. Therefore, charging begins and this plate acquires positive charge and plate B acquires negative charge and charging continues until it becomes 6 volts. Therefore, here we say maximum PD across the capacitor is V naught. Let us say it will be V naught. How much? 6 volts. If it is 10 volts, it is charged up to 10 volts. If it is 12 volts, it is charged up to 12 volts. So, charging, full charging takes place. After complete charging, you disconnect this terminal. This is disconnected and we connect Y and Z. These two are connected. Means charged capacitor is now connected to inductor. And now onwards, this is not required. It is only for initial charging. Therefore, take out this one, not required. So, we have got a charged capacitor connected to inductor. Now, we know discharge begins because it is a closed circuit. Discharge takes place through the inductor, remember. And actually what is happening, from the plate B, electrons they travel through the circuit, through the inductor, and they come to the plate A, thereby neutralizing the positive charge on the plate A. So, electrons are going from plate B to plate A, but we explain everything in terms of flow of positive charge, conventional current. Therefore, conventional current or flow of positive charge is taken in the opposite way. So, we simply say that positive charge flows like this, thereby amount of charge in positive charge flows from A to B, and as charge flows from A to B, plate A loses the positive charge, plate B also loses negative charge, neutralization takes place. But flow of positive charge in this direction clockwise, is it not a conventional current? Yes. So, it is known as a discharge current. It is known as what? Discharge current, and current flows in this direction. It is a discharge current, and discharge current starts to increase, because whenever you connect Y and Z, discharge current is 0, but it starts to increase. And as the current starts to increase, here amount of charge decreases. And when current flows through the inductor, there it produces magnetic flux, remember. It produces magnetic flux goes on, increases. And when magnetic flux goes on, increases, it is the change of the magnetic flux which produces EMF here. EMF is induced, and that EMF is the opposing EMF which opposes the growth of the current. Therefore, it is a plus, it is minus. Therefore, current, discharge current increases, but that increase of current is opposite, remember. Hence, discharge is what? Somewhat, it is slightly slow, remember, compared to, otherwise it is instantaneous, but now it takes more time, because EMF opposes. Anyhow, current goes on, increases, and amount of charge goes on, decreases. And if you observe this one, the graph will be like this. Growth of the current. Then at one instant, when current becomes highest, here charge becomes 0, because it is fully discharged, remember. Therefore, whenever current becomes highest, then at that time charge in the capacitor becomes 0, and we get the graph like this. Okay. Now, current is I naught. For moment, current is I naught, and magnetic flux is maximum. When magnetic flux is maximum, inductor is storing maximum energy. What is the formula for energy stored? Half L I square. If current is maximum, energy stored is also maximum. What is the energy stored in the capacitor? 0. So, can we say energy is totally transferred from capacitor to inductor? Yes, and we get the graph like this for the current. It is known as a discharge current. Now, see, current cannot increase further, current it has to decrease, because there is no charge. Therefore, current starts to decrease, decay of the current. Due to the decay of the current means here magnetic flux must disappear. So, now magnetic flux disappears, remember, decay of the magnetic flux takes place. During the decay of the flux, we know it is the change of the flux and EMF is induced, and EMF reverses the polarity. EMF reverses the polarity, and here this becomes plus, this becomes minus. So, as the magnetic flux suddenly collapses, because there is no current, remember, current is highest, but there is no further current. Therefore, all of a sudden flux dies out. When magnetic flux decreases, it produces EMF, EMF reverses the polarity, and now this EMF produces the current, and current flows from positive to negative, means current still flows in the same direction. Therefore, conventional current flows like this. Therefore, this plate acquires a positive charge, remember, and this plate acquires negative charge. Here positive charge is added, from this plate positive charge is taken out. conventional current I am telling, okay. But as a capacitor is charged, its potential difference goes on increases. And when potential difference between the plate increases, capacitor opposes further charging. So, that is why in the beginning you have got a more current, but because of potential difference across the capacitor, it opposes the further charging. Therefore, strength of current goes on decreases, but current is positive, remember. Therefore, we get the graph like this. Current decreases, and moreover here magnetic flux is also decreasing. Flux decreases, and at one point flux becomes 0. When flux becomes 0, what is the induced EMF? Induced EMF is also 0. So, EMF is 0, and now at that time capacitor is fully charged, remember. Capacitor is fully charged, but with one difference. What is the difference? Plate B is positive, plate A is negative. Therefore, from here to here it is due to the discharge of the capacitor, and this part is due to charging of the capacitor. Got it? And this charging current produced by whom? EMF in the inductor due to the decay of the magnetic flux. Now, discharge of the capacitor again begins. So, actually electrons from the plate A, they come to the plate B, thereby neutralizing the positive charge. But to explain in conventional, in the form of conventional current, we say positive charge from the plate B goes to the plate A, but it flows through inductor. Therefore, now positive charge flows in this direction, and conventional current is also in the same direction, conventional current. Therefore, now again discharge of the capacitor begins through the inductor, and as discharge begins, here magnetic flux starts to increase, remember. Magnetic flux increases, and that increase of flux produces EMF. This EMF opposes the increase in the current. Therefore, for this EMF, this must be positive, this must be negative. It opposes, remember. It opposes discharge of the capacitor. Therefore, discharge of capacitor is not quick, it takes some time, it is delayed, remember. And compared to earlier case positive charge flows clockwise, conventional current flows clockwise. Now, we say positive charge flows in the anti-clockwise direction, conventional current must be in the opposite direction. And moreover, as a capacitor is undergoing discharge, amount of positive charge here decreases, amount of negative charge decreases in another plate, and here magnetic flux goes on increases, and we get the current like this, because current is now negative. And at one point capacitor is fully discharged, but whenever it is fully discharged, at that moment current in the circuit is maximum, because current is increasing, discharge current. Here charge becomes less and less. Whenever this becomes almost 0, at that moment current in the circuit is maximum, that is minus I naught, that is here minus I naught. It is due to the discharge of the capacitor, but in the opposite direction compared to earlier case. Now, can current increase further? No. So, therefore, this current suddenly becomes almost 0, then here magnetic flux has to disappear, because for the current I naught, here you have got a highest flux, that flux must disappear, means decay of the flux takes place. Due to decay of the flux, due to the decay of the flux, EMF is induced. Magnetic flux goes on decreasing, and when magnetic flux goes on decreasing, EMF reverses the polarity, EMF reverses the polarity, therefore, this becomes negative, this becomes positive. and now this decay of the flux, magnetic flux produces the current. This EMF produces the current, and we know the conventional current is always from positive to negative like this, means still current flows in the same direction. And here positive charge added to the plate A, and here positive charge is taken out, therefore, plate A acquires positive charge, here positive charges are taken out conventionally, therefore, it acquires negative charge. Okay. But as a capacitor acquiring the charge, between the plates voltage increases. As voltage increases, it opposes the further charging. Therefore, strength of current in the circuit decreases. Charging current goes on, decreases, and current flows in this direction, conventional current. Charging current flows in this direction, it goes on, decreases, and at one point flux becomes 0. Magnetic flux through the inductor becomes 0, EMF becomes 0. But at that time capacitor is fully charged, but strength of current, charging current goes on, decreases, and we get the graph like this. This is the graph. Now you see, is it not it looks like alternating current, and here capacitor is now fully charged, and what is the energy stored in the inductor? 0, but that energy is completely now transferred to capacitor, and energy stored in the capacitor is maximum. Now process continues. It is as good as initial condition, where plate A is positive, plate B is negative. Again discharge begins, conventional current flows in this direction. Due to that, conventional discharge current increases, magnetic flux increases, and increase of the flux produces EMF which opposes the discharge current. Therefore, discharge is somewhat delayed, and we get the graph like this graph. And whenever current becomes highest, at that moment capacitor is fully discharged. Then the magnetic flux here starts to decrease, there is a decay of the magnetic flux which produces the current, and current flows in the same direction. Therefore, B becomes a positive, A becomes negative, we get this graph, this part of the graph. So, that process continues, and what is interesting here, at one instant energy stored in capacitor, at another instant after some time it is fully stored in inductor. Here it is stored in the form of electrical potential energy, and here it is stored in the form of magnetic potential energy in magnetic field. Therefore, transfer of energy takes place from capacitor to inductor, inductor to capacitor. But practically this type of transfer takes place, no doubt, but practically we never get output like this continuously. The reason is inductor coil has got a resistance, remember, and we know in the resistor it produces heating effect. Therefore, there is a loss of energy in the form of heat. Therefore, practically we never get this type of oscillation continuously. We have to make some modification, then we can get, that is known as oscillator circuit. But if you do this experiment like this, then with the time the strength of current goes on, decreases. It is a type of damped oscillation that is studied in first PU. So, this is what is actually happening practically because of the resistance. Now, we derive the formula for current produced in the LC oscillation. at some instant. See, the process continues and discharging continues. At one instant, let us say V is the potential difference across the plates of the capacitor and E is the induced EMF in the inductor. Q is the instantaneous charge. Remember, it is in between at some instant. Now, we know there are two potential differences, one this potential difference in the circuit and another one is induced EMF. So, there is no resistance, therefore, algebraic sum of EMFs in the circuit is equal to what? Algebraic sum of product of current and resistance, Kirchhoff's voltage law. So, I am applying that equation. So, V plus E must be equal to 0 because there is no resistance. Now, V means what? Voltage across the capacitor, that can be written as Q by C plus this is induced EMF. What is the formula for induced EMF? It is minus L di by dt is equal to 0, that already we know. Now, what is this di by dt? Rate of change of this current, either charging current or discharging current, it continuously changes and we know what is the formula for current. Current is given by the formula dq by dt, rate of flow of charge, but in this case we put minus sign. The reason is very simple. Think that here amount of charge decreasing, at that time strength of current is increasing, or later if capacitor is charging, at that time amount of charge increases, strength of current decreases because capacitor opposes, therefore we put minus sign. So, substitute this one here. So, therefore, Q by C plus minus L, instead of I we write minus dq by dt, therefore, it is d by dt of minus dq by dt is equal to 0. Q by C minus minus becomes plus, it is d square q by dt square into L. Now, you throw out is equal to 0. Okay. Now, you divide it by L. So, it is q by LC plus d square q by dt square is equal to 0, or I will write this term first, d square q by dt square plus q by LC is equal to 0. Okay. Now, in first P you studied about simple harmonic motion, SHM. In the case of SHM, you have got a equation for acceleration. What is the equation for acceleration? So, in SHM, acceleration is given by the formula minus omega square x, where x is the displacement from the mean position, a is the acceleration, omega is the angular frequency. Acceleration can be written like this, dv by dt, rate of change of velocity, is equal to minus omega square x. Okay. But dv by dt can be written as d square x by dt square, isn't it? And you bring this term to left side, plus omega square x is equal to 0, because velocity is equal to dx by dt. So, substituting here. So, this is the formula which holds good for SHM. Now, you compare both the equations, are they not alike? See, here it is d square x by dt square, here it is d square q by dt square, and here you have got x, instead of that here you have got q. Therefore, just by comparison we can write omega square is equal to 1 divided by LC, or what is omega? Angular frequency is equal to 1 divided by root LC. This is the equation for angular frequency of the alternating current produced in LC oscillation. Now, omega can be written as 2 pi f naught is equal to 1 divided by root LC, or f naught is equal to 1 divided by 2 pi into root LC. So, this is the equation for resonant frequency of LC oscillation, and this equation is similar to resonant frequency of LCR circuit. Got it? Therefore, if you know that formula, resonant frequency of LCR circuit, for LC oscillation also the formula is same. Okay? And this particular frequency is known as resonant frequency of LC oscillation, and we can write it as omega naught. Instead of omega, we can write it as omega naught. Now, we solve one problem from old question paper. An inductor and bulb are connected in series to an AC source of 220 volts 50 hertz. A current of 11 ampere flows in the circuit and phase angle between voltage and current is pi by 4 radian. Calculate impedance and inductance of the circuit. So, this is from old paper July 2016. So, I said problems need not be only on LCR, it may be CR circuit, LR circuit, like that. See here, an inductor means L and bulb means resistance, therefore, it is which circuit? LR circuit. So, first we note down the values. Vrms that is 220 volts, and what is the frequency of AC? 50 hertz. A current of 11 ampere flows in the circuit. They say current, it is IRMS. They need not say that IRMS current, no, current means IRMS, it is 11 ampere. Okay. And what is the phase difference between current and voltage? It is pi by 4 radian, that is pi by 4 radian, which is equal to 45 degree. Calculate impedance of the circuit and inductance of the circuit. So, these two values you are asked to find out. Okay. Now, first of all we take phase difference. So, I am writing the equation for tan phi. Tan phi, it is which circuit? It is LR circuit. Therefore, tan phi is equal to XL by R, or tan 45 is equal to XL by R. Tan 45 is 1. Therefore, we can say XL is equal to R. Inductive reactance and resistance are equal. This is one part of the problem. Now, we know current in the circuit, voltage in the circuit, RMS values. If you divide them, voltage by current is nothing but impedance of the circuit. Impedance of the circuit is equal to Vrms by IRMS. 220 volts divided by IRMS 11, it is equal to 20 ohms. Therefore, now impedance of the circuit is 20 ohms. Okay, that is another point. Now, what is the formula for Z? Z is given by the equation square root of R square plus XL square, because it is RL circuit. But we know inductive reactance and resistance are equal. Therefore, Z is equal to square root of, instead of R square I can write XL. Therefore, it is XL square plus XL square, that is 2 XL square, square root of 2 XL square. Now, square both the sides, Z square is equal to 2 XL square, or what is XL? XL is equal to, take square root, it is Z divided by root 2. Now, inductive reactance is equal to Z. What is the value of Z? 20 ohms divided by root 2, and if you find out, it is 14.14 ohms, 14.14. Okay. But we know inductive reactance is always equal to 2 pi FL, 14 point, that is 14.14. 2 pi FL is equal to 14.14. L is equal to 14.14 divided by 2 pi F. 2 into 3.14 into 50. That last answer is 0.045 Henry. It is the answer. This is one more problem from old paper. A sinusoidal voltage of peak value, see here, peak value 283 volts and frequency 50 hertz is applied to a series LCR circuit in which R equal to 3 ohms, L 25.48 millihenry and C is equal to 796 microfarad. Find impedance of the circuit, phase difference between voltage and current, power factor of the circuit, average power dissipated in the circuit. This is actually from March 2015, but same type of problem asked in the year March 2017, June supplementary 2019 and last supplementary exam September 2020. So, all are the same type of problem. So, very important one, it is on LCR circuit. Okay. Now, first of all we note down the value, a sinusoidal voltage of peak value, therefore, it is V naught. V naught is equal to 283 volts. What is the frequency? 50 hertz. And what are the values of LCR? Resistance is equal to 3 ohms, L 25.48 millihenry, C capacitor value 796 microfarad. Okay. Now, we find out one by one. First question, impedance, it is the LCR circuit, therefore, what is the formula for impedance? Z is equal to root of R square plus XL minus XC whole square. Therefore, we find out inductive reactance 2 pi Fn, that is 2 into 3.14 into 50 into 25.48 millihenry 10 to the power minus 3. And if you solve this one, it is 8 ohms. Next, capacitor reactance XC 1 divided by 2 pi FC, 1 divided by 2 into 3.14 into 50 into capacitor value 796 into 10 to the power minus 6, and its value is 4 ohms. Now, we find out impedance of the circuit. Z is equal to square root of R square plus, here inductive reactance is a higher value XL minus XC whole square. Even if you write XC minus XL, it is correct, because it is anyhow square, it is always positive. Square root of R, resistance 3 square plus this is 8 minus 4 whole square. 8 minus 4 is 4, square is 16 plus 9, 25. Therefore, Z is equal to 5 ohms. We got the answer for first question, impedance of the circuit. Now, next step we find out phase difference. How to find out phase difference? So, phase difference between current and voltage. So, we know phi equal to tan inverse of XL minus XC by R. Phi equal to tan inverse of, it is 8 minus 4 by 3. 8 minus 4 is 4, this is 4 numerator, denominator is 3, 4 by 3 is 1.333. Therefore, phi is equal to tan inverse of 1.3333 or phi, it is 53 degree 7 minutes. So, we got phase difference between current and voltage. Next step, power factor. Third one is power factor. Power factor cos phi you can find out, no doubt, cos phi, because phi is known. It is cosine of 53 degree 7 minutes, and you refer the log table, you will get the answer. But instead of referring the table, it is better to solve this one. Power factor of any circuit is equal to R by Z, no need of referring the log table. What is the value of R? 3. Z impedance, impedance is 5.6. Power factor is 0.6, it has got no unit. And the next one, it is average power dissipated in the circuit. So, we find out average power dissipated, P average. So, fourth one. What is the formula for average power dissipated? Only resistor can produce a heating effect, resistor consumes energy. Therefore, power dissipated in the circuit is equal to I RMS square into R. So, we can solve this equation. But how to find out I RMS square or I RMS? That is the question. Therefore, I RMS is equal to V RMS by Z. But here which value is given? V naught, not V RMS. What is the equation for V RMS? V naught by root 2. V naught by root 2 into Z. So, substitute I RMS equal to V naught 283 divided by root 2 into Z. What is the value of Z? 5. And that comes to be 40 ampere. Now, P average is equal to, it is 40 square into resistance 3. So, that comes to be 4800 watts. So, this question or similar type of problems already asked number of times, remember 1, 2, 3, 4 times. So, very important one. One more problem from old question paper. A sinusoidal voltage of peak value 285 volts is applied to a series LCR circuit in which R equal to 5 ohms, L equal to 28.5 millihenry and C is equal to 800 microfarad. Find first one resonant frequency, second one impedance, current and power dissipated at resonance. It is from June 2017. Okay. Now, we note down all the values. Peak value is given again V naught, how much? 285 volts. Frequency, you are asked to find a resonance frequency. Okay. R equal to 5 ohms, L 28.5 millihenry, 10 to the power minus 3, and capacitor value 800 microfarad, 10 to the power minus 6 farad. Okay. First question, resonant frequency. F naught is equal to 1 divided by 2 pi root LC, 1 divided by 2 into 3.14 into root square root of L 28.5 into 10 to the power minus 3, capacitor value 800 into 10 to the power minus 6. It is 33.35 hertz. So, resonant frequency we got. Second one, impedance, current and power dissipated at resonance. So, it is very simple. At resonance, impedance is equal to what? Resistance of the circuit, because current and voltage are in phase and it acts as a resistor circuit. Therefore, Z minimum equal to R. What is the value of R? 5 ohm. So, we got impedance, then we find out current, IRMS. Current means IRMS is equal to VRMS by Z minimum. But what is Z minimum? Z minimum is R. Okay. But here instead of RMS value, peak value is given, therefore change it. It is V naught by root 2 into Z minimum, 285 divided by root 2 into Z minimum 5. That comes to be 40.3 amps. Okay. Then power dissipated at resonance, P average is equal to I RMS square into R. What is the current at resonance? Current at resonance is 40.3 square into resistance 5 ohms. So, it comes to be 8,122.5 watt. This is the answer. A resistor 100 ohms, pure inductance coil of self inductance 0.5 Henry and capacitor are in series in a circuit containing an AC source of 200 volts 50 hertz. In the circuit, current is ahead of voltage by 30 degree. Find the value of capacitance. So, it is again LCR circuit where it is not under resonance. Instead of that particular case is given. In this circuit especially, current is leading the voltage by how much? 30 degree. So, it is the specific case. First we note down the values. R 100 ohms, L 0.5 Henry, capacitor value you want to find out, and voltage is given 200 volts, that is VRMS. Frequency is given 50 hertz, and in the problem it is clearly given I current leads V by 30 degree, implies that Whose property dominates? Capacitor property dominates, because if capacitor reactance is more, then only current can lead the voltage. Therefore, XC greater than XL and phase difference is 30 degree. Okay. Now, self inductance is known, frequency is known, we can find out inductive reactance 2 pi FL 2 into 3.14 into 50 into 0.5 Henry. That answer is 157 ohms inductive reactance. Okay. Next, phase difference is known, and even we know capacitor reactance is greater than inductive reactance. Therefore, we use this formula, tan phi is equal to, it is XC minus XL by R, or tan 30 degree is equal to capacitor reactance we have to find out minus inductive reactance 157 by R. R is 100 ohms. So, I am simplifying this one. XC minus 157 is equal to 100 into cross multiply, tan 30 is 1 by root 3, and if you find out capacitive reactance is 214.7 ohms. But what is the formula for capacitive reactance? 1 divided by 2 pi Fc, or C is equal to cross multiplication, C is equal to 1 divided by 2 pi F into XC, 1 divided by 2 into 3.14 into 50. What is the capacitor reactance? 214.7. And if you find out the value of C, it is 14.83 microfarad. This is the answer. We take one more problem. Obtain the resonant frequency of a series LCR circuit with the L equal to 4 Henry, capacitance equal to 27 microfarad and R equal to 8.4 ohms. What is the Q value of the circuit? Also find bandwidth. Q value means quality factor or sharpness of the circuit. This is for 5 marks. It is actually from March 2014 and same type of problem again asked March 2016, but values are different, same type of problem. So, first we note down the values. L 4 Henry, capacitance 27 microfarad, R 8.4 ohms. I want to find out resonant frequency. F naught is equal to 1 divided by 2 pi root LC, 1 divided by 2 into 3.14 into square root of L and C, 4, 27 into 10 to the power minus 6. It is 15.32 hertz. Answer. Resonant frequency we got. Then next step is to find out quality factor. So, quality factor you can use any formula. There are number of equations. It is one of the equation, 1 by R into root of L by C, 1 divided by 8.4 into square root of L. L is 4 Henry divided by, this is 27 into 10 to the power minus 6, value of C. If you solve this one, it is 45.82. It is a number, no unit, remember. Quality factor we got. And next step is to find out bandwidth. How to find out bandwidth? We know quality factor is also equal to omega naught divided by 2 delta omega. What is this 2 delta omega bandwidth, which is equal to omega naught by q. How to find out omega naught? 2 pi f naught by q, quality factor. Therefore, it is 2 into 3.14 into resonant frequency 15.32 divided by quality factor 45.82, and this comes to be 2.1. What is the unit? It is the ratio of the, it is the bandwidth, therefore, it is radian per second.